for.
This meeting is being recorded.
So welcome everyone to our Dark Energy Explorers Zoom night. We are super excited to have you. And thanks for spending your Monday night after the Super Bowl and before Valentine's Day with us. We hope that you guys will enjoy tonight, learn something new, get to hear from us. But we are super thankful for all of the work that you guys have done so far, and the participation that you guys have had in this project has been super awesome. And we can't thank you guys enough for being a part of Dark Energy Explorers. And we are going to talk a little bit tonight. We're going to learn about a logo design competition that we are doing. And thank you for those of you who have already submitted some designs. We're still going to keep it open for a few weeks and take some designs. So we would love to have those. We are going to introduce you guys to some of our team members who are here tonight. And then we are going to go through with Jose some classifying. We're going to get to learn a little bit about the history of HETDEX, the Hobby-Eberly Telescope Dark Energy Experiment. And this is the telescope in my Zoom background behind me. And then I'm going to talk a little bit with you guys about what we actually do with your classifications once we get them. What happens to them once you guys finish swiping back and forth and we finally get them. And then last but not least, we're going to just have a Q&A. Maybe we'll go through some classifications together, but we want to make sure that we can answer any questions that you guys have for us here tonight. So without further ado, I am Lindsay House. I am the graduate student lead of Dark Energy Explorers, and I am a third-year graduate student at UT Austin here in Texas. That's where I am right now. And yeah, I will let Karl introduce himself.
Hi, y'all. I'm Karl Gebhardt. I'm the PI of HETDEX. I've been working on this for a long time. It is, I just want to say a big thank you for all the work you've done so far. It has been very useful, and we will tell you about that and how to, and we want to encourage you to keep going because we love it.
Hi, hey everyone, I'm Erin Menta Cooper. I'm the data manager, and I've been working on Zooniverse and Dark Energy Explorers along with Lindsay and Karl and the rest of the team for a while. We're really excited to have you all here. We've been going through all of your results, and it's really been helpful. So I, organize all the data, and I help to put the sources you guys have been classifying into our catalog. So it's so great to meet you all. Hi.
Awesome. Yeah. And then Jose, would you like to go ahead?
Yeah. So hey y'all. These three, Mike, Jose, and Mike, Isaiah, and I, we're all undergrads. I'll let them introduce themselves in a bit. I am a third-year astronomy major. I'm also pursuing a teaching certificate in physics. So my focus with HETDEX and Dark Energy Explorers, which I joined approximately like half a year ago, is focusing on the education and project outreach for our team. And I will now mute.
Awesome. Thanks. How about Isaiah? You want to go ahead?
Yeah, hey everyone. My name is Isaiah. I'm a third-year physics and astronomy double major. I do the machine learning aspect of our project. I just want to personally thank y'all for all the work you've been doing. It's making our job a lot easier, my job a lot easier, and I'm looking to continue to work with you all.
Thanks, Isaiah. Mike?
Hi, my name is Mike. I am a third-year astronomy and physics major, also at UT. And I work with user database analytics and data visualization for like whatever like it does with like a account and like all of the classification numbers that you guys have done. And like it's always so fascinating to like just work hands-on with all of these data, because like we have more than 4 million classifications, which actually still blows my mind. Like I'm very grateful. We are also very grateful for like what all of you guys have been doing. So please keep it up, because we're like really excited.
Awesome. Thanks, guys. Yeah, so first and foremost, we also wanted to invite you guys to submit logo designs. If any of you guys have an artistic bone in your body, you can let your imagination run wild, and feel free to submit it to that email address, lindsay.house@utexas.edu. But we will keep that open and remind you guys also at the end of the meeting. And so what we are going to start with here tonight, we're going to go through some practicing, some tips, talking about how we tackle the dark energy problem, and then how your classifications help us so much with actually understanding what dark energy is and conducting the science that we do here with our telescope. So with that, I will let Jose introduce you guys and go through some practicing of some of our examples.
Yeah, so we're gonna have a few examples of some of the classifications. These are actually gotten from the talk discussion board that all of you citizen science volunteers help us out on the Zooniverse page. So they're handpicked from discussions that we've had with you, so we're excited. So this is one of the first classifications that we have. I would like you all to use the chat function, and I'll give you some like 30 seconds or so, but feel free to tell us if you think it's a keep this galaxy or throwback, which are the usual hashtags that you use in this type of classification on the app or website, whatever you use. So feel free to tell us what you see and what you think this would be classified as. And you can go ahead and kindly unmute by using the raise hand function if you'd like to. If not, go ahead and keep using the chat function. You can also unmute to discuss. So we would like to hear what you're looking at, any sort of thing like that. And for those that are putting throwback, I know some of you have already told us why. Oh, Diana, I'm sorry, I'm not sure which way, but would you like to share what you think?
Yes, this is the only way I learn is by just saying what I think and then probably being wrong, but I'll do it for the group. So I think I would be confused normally on this one because the line, I forget what the terminology is, but the lines don't totally match up, but they kind of do. The spectral lines at the bottom, the graph.
The bottom left one?
Yes, the bottom left. So they're not totally on that line. And I don't really see anything in any of the boxes, the colored boxes. So I think the graph might throw me off, but I would say I don't see anything based on those other boxes, the colored boxes.
Okay.
So I would say throwback.
Okay, throwback. Okay, thank you. Anybody else want to share their opinion as to why unmute or put it in the chat before we say what it is? All right, so yeah, bottom right window. Okay, yeah, thank you, Mikael, not sure which one, but yeah, thank you. So this classification is a hashtag throwback when you're like classifying. So yeah, so that is the right type of idea. The bottom left has a lot of the error curves are too big, but the main indicator of why this would be a hashtag throwback when you're classifying as a volunteer is because there's no bright indicative spot on the bottom right corner. That's the one that has the red square, and there you see like sort of neon colored. Usually you see a bright spot there, as well as the one that Deanna pointed out, the top left. Um, they don't have like that dot, that spherical dark circle that we want to see to immediately say this is a good data or bad data. So this would be bad data, and we would throw back. So we're gonna go ahead and look at the next detection. Maybe thank you for all of y'all that are still discussing. All right, so this is a different one. This one might be tricky. We'll see. So tell us why you think it's a keep, and then say whether it's a keep or throwback, and then tell us why. And as well, if anybody wants to raise their hand or unmute and explain why. I'll give it another 20 more seconds so people can still keep looking at the image. All right, now that I've had some of you think about it and share, would anyone like to unmute? Would a team member like to unmute and explain their reasoning and what it is?
Sure. So this is a beautiful one for me. This is like a textbook Lyman alpha emitter. It's those the code that we do. I call it looking for dots, and in that panel on the left, those four boxes on the left, we're trying to find a kind of a circular dot. Doesn't have to be in all of them, but at least the top one and maybe the top two, and then have a nice line. And many people said the proper reasoning in terms of that line on the bottom and those dots in the middle. Exactly.
All right. So yeah, that is exactly what we look at. Thank you, Dr. Gebhardt, for sharing. We're now gonna go. We're now gonna look at another classification and see whether it's keep or throwback. And as well, the same reasoning, share in the chat what you think it is and explain it. Tell us exactly like maybe what you look at, just how we've looked like the top left, bottom right, all of that thing. I'll give y'all another like 15 seconds, but we're definitely gonna discuss a bit more. We'll see in a bit. Let's see. And remember, it's swipe right or left if you're using the app or on a desktop computer, keep or throw back. So if you think it's a black hole or other things, errors, tell us whether you would keep it or throw back.
Mark thinks it's a pigeon.
Yeah, it's wings spread, and we took an image of it with the HETDEX. All right, so thank you all for sharing whether it be a throwback or keep. Let's see. There's a lot of frisbee or maybe a bird. There is a lot of throwback. We do have a few keep by Vaughn. So yeah, so this one might be tricky. So if y'all have been classifying, once you reach a certain amount of classifications, you get a pop-up that says black hole. This is the image that we get. It's a wide spectra curve and stuff with the error on the bottom left that you see. And the fiber cutout images, the ones that you see on the top left areas, usually have a wider spherical elliptical, no, spherical dot that's darkened. So yeah, so this one would actually be keep this galaxy classification, and it would indicate that it is a black hole. So y'all are correct. It would most likely fall as a black hole. However, when you're swiping right or left, we do want to keep this type of data when you're classifying on Zooniverse. Although it's a black hole, it is still data that is very important for us here with HETDEX in the machine learning. So why is it a keep this? And why does it follow a black hole? So it's most likely a black hole, as I said, because it's wide and those error values are so small and almost it's like a perfect plot that we want to see. And apart from that, we see that bright indicative spot on the bottom right that we want to look at, that we want to get. So although it may be confusing, yes, this is a black hole most likely, but we do want to keep this. We as the astronomers that are visualizing and using this data do want to look at this and keep it. So as you go back to classifying and stuff, keep this in mind. Black hole imagery is something we want to keep. But if you have any questions as well, please let us know. We will have a discussion time at the end.
So Jose, one comment on one additional comment is that we realized with these black holes that we didn't have quite the proper training examples when we initially launched, and these are just prime examples. These what we're after is objects that just trace where the matter is in the universe, and black holes are objects that are inside of massive galaxies, and so they're actually beautiful tracers of what we're after, of what we're trying to get after. So not only do we want to keep them, but we want to study these more in detail, and so that's why these black hole images are some of the more important in the data set.
Yeah, and it's totally okay if some of you guys have thrown these back in the past, that it's still helpful for us to see and learn from you guys that this is confusing and so that we need to clarify. So because of you guys, we actually added part of this into the tutorial because it was confusing. So yeah, it's still helpful for you guys, even if we threw some back.
Yeah, another thing to clarify, these images, when you classify, don't feel pressured if you throw back or keep. They are averaged out with the users that are using Zooniverse. So if you threw it back, don't worry, there was other users that also were classifying this type of image as well, maybe at the same time. So that's how we take our data and average, but we'll talk about that later on with Lindsay as well. So just wanted to do that. And Diana, to answer your question, there's only one workflow at the moment, which is either keep or throwback. So that should clarify that question.
All right, so here we have, let me pause this for just a second. Yeah, I'll let you go ahead, Jose.
Okay, so how does this connect? What is dark energy? What is dark matter? What is any of this? How are we using your data? I'm gonna do a brief intro on this. We're gonna have a little short animation. So sit back, watch it, and we'll discuss in a bit. Let me mute back.
60-second adventures in astronomy.
Can you guys hear that okay?
Yes, loud.
Number 9, dark energy. Why is the universe expanding? Albert Einstein was absolutely certain the universe was stable, but he couldn't work out why his snazzy new relativity equations suggested that it was contracting. So Einstein figured space must have an inbuilt tendency to fling itself apart, which would balance out the pull from gravity. This flingy outness got called the cosmological constant and meant the universe could be kept static, which was great until it was proved by Edwin Hubble that the universe is in fact expanding. And that cosmological constant became what Einstein described as the biggest blunder of my career. Then in 1998, scientists discovered that the universe was not only expanding, but that expansion was actually getting faster. So either space does have a tendency to fling itself apart, or there must be some other hidden weird stuff in the universe causing it, referred to as dark energy. Astronomers are looking for it right now by measuring tiny kinks in space. And in its simplest form, this dark energy is pretty much a cosmological constant. So Einstein was right all along, apart from the time he said he'd blundered, the big thicko.
All right, so that was a fun little 60 seconds. Could you believe that you got all that information in 60 seconds? Yeah, so dark energy. So this is a quote from Dr. Karl Gebhardt, who is obviously the lead in the research. So it is, the phrase dark energy is indicative of our misunderstanding of how the universe expands over time. Dark energy may not be dark and it may not be energy. It's the phrase we use to explain our ignorance. So we just use this phrase and we calculate it and such, but the next slide will go over this. So I will let Lindsay switch this on. And Dr. Gebhardt will definitely be talking right after this, so stay tuned for that. So dark matter, dark energy, they are not the same. So what's the matter? So basically, dark matter is was found by Vera Rubin in the early 20th century, sorry, in 1940s, I believe, 1950s. Basically, so Vera Rubin looked at a catalog of galaxies that are like Milky Way, like our galaxy. And by categorizing and looking at the mathematical evidence, there was certain discrepancies in their rotational speeds that they were calculating. There was supposed to be more mass to account for this speed that they saw. So basically, there must be something else. There must be more mass. Vera Rubin then accounted and was the first person to say it's dark matter. And by using this constant, this value, it then accurately portrayed the rotational speed of these galaxies at the time from that catalog. So, as I said, that is dark matter. It is different from dark energy. If we look, before continuing with dark energy, if we look at the right pie chart, 5% of the observable matter makes up 5%. That is the galaxies, things that we see. Well, dark energy, dark matter is in galaxies, but basically we can't really see those things. So dark matter accounts for 25% and dark energy is 70%. So that's a huge chunk that we're not able to see at all. So basically, dark energy is a name given to the mysterious force that's causing the rate of the expansion of our universe to accelerate over time, rather than to slow down. Basically, when the Big Bang Theory came up, the expansion of the universe was thought to be finite or to some sort of constant. Dark energy accounts for this acceleration that's faster, that is increasing, that makes us account for all of these things that we see. That's sort of a short intro, and I may have been wrong or I may have forgotten like crucial information, but don't worry, fret not. Dr. Karl Gebhardt is coming up and he'll be able to discuss more and clarify any questions that you may have.
Awesome. Thanks, Jose. Yeah, so now I would love to turn it over to my advisor, Karl Gebhardt.
Okay, so let me tell you a little bit about HETDEX and why your input is having such an impact. So HETDEX is the project that I came up with the idea in 2002, which is a long time ago, over 20 years ago, just to give you a feel for how long it takes to do something major like this. And it ended up being about a $42 million project. So the answer is a 42, obviously, if you have a question there. Right now we're about 60 to 70% complete at this point with the data, and we're going to finish in 2024. Let me explain what we're doing. Because we're trying to understand the expansion of the universe, we need a huge survey of the sky. HETDEX has taken an approach that's very different from all the other experiments out there. All the other experiments are looking relatively nearby in the nearby universe, and what I mean by that, only about maybe 3 to 4 billion years ago. HETDEX is looking 10 billion years ago. And so what we do is we look at how fast the universe is expanding 10 billion years ago. You compare that to how fast the universe is expanding 3 billion years ago. It's the differential that really matters for what is causing dark energy. Well, where you come in is that HETDEX is a huge survey. We built this huge instrument. It's the largest spectrograph on the planet, where a spectrograph just takes some bits of area of the sky and breaks it into a prism effectively. And we were going to look through all of our data that's being put on a incredible number of CCD devices. What the base observation we get is a spectra that is being put on something very similar to what's in your cell phone camera. It's a CCD device. And we look through that and then we try to find dots. Just to give you the numbers, we are looking through about 1 trillion resolution elements, one trillion of these elements, and we're trying to pull out 1 million of these galaxies that are in the distant universe. Well, when you look through 1 trillion things, and we have code obviously that do that. We use the TACC, the Texas Advanced Computing Center, one of the most powerful computers in the world. We have code and we try to find these 1 trillion resolution elements. We find noise. There is lots of instrumental noise. There are high energy particles, we call these cosmic rays, that come in and they make a big splash that kind of looks like one of these dots. And there's many artifacts. When you're looking through 1 trillion things, you find a lot of artifacts. And we built the instrument with as uniform as we possibly could, but we could only get down to such a level. That's where you come in, and that's where we're using a combination of machine learning, AI, plus visual vetting, which is what you are doing. I have probably looked through, I don't know, probably up to 50,000 or so sources. We have one of our colleagues, she's probably looked through 100,000 at this point individually. We look through a lot, but there's no way we're going to get through the many millions of sources. And it's your collective, the eye is just remarkably powerful at finding correlated pattern, correlating noise. Then we tie what you're doing into machine learning, and that's where Lindsay's going to talk a bit about. It's one of the things that I kind of love is that you are having a direct input into this $42 million experiment that's trying to understand what the universe is doing 10 billion years ago. So that's just to put it in context. And I was, when we first came at this, I was kind of saying, well, maybe the AI, machine learning, the algorithm will be far superior than the human eye. And I said, well, let's test it out and see what we get. And I was just so pleasantly surprised that if we take your average accuracies and compare it to somebody within the team, myself, or anyone who's talking here, it's remarkably consistent. The accuracy that we're getting from your collective understanding has been very impressive. That's kind of what Lindsay is working on. Okay, so let me end there so then we can talk more about your input. But it's been great.
Cool. Thanks, Karl. Awesome. So I am going to talk a little bit, about what we do with your classifications once you guys finish swiping. What do we do after that? They come to us, and then what happens? So Karl talked about HETDEX and how we're collecting all of these elements from our telescope. We're going to have about 1 trillion of these elements that we're going to search through, but we're really focused on only finding about 1 million of those galaxies. But 1 million is still a lot, right? And we want that sample of galaxies to be the most pure sample as possible, right? We want to get out all of those bad detections that, you know, might be the bird or, you know, those different bad things that can happen to our telescope that aren't those pretty galaxies that we saw in our examples that Jose showed. So how can we do this? And that's where we turn to you guys for Dark Energy Explorers. So you guys have been doing this and helping us with this. And so by classifying these real galaxies to keep, we're putting those and keeping those in our sample to use for our science. And then the ones that are bad, we're trying to get those out. And so how we're doing that is that whenever we get a classification from you guys, we have at least 10 of you look at one source. So don't worry if you guys accidentally, you know, it was a tricky one, you accidentally said throw back, maybe you weren't sure, you said keep. We have at least 10 of you look at each of these sources to build in some of that reliability so that sometimes it's even hard for us. Sometimes we make mistakes, like you were saying, it's so hard. So compared to us here as like HETDEX astronomers on the team, you guys are 92% accurate compared to us in finding those false positives. So that's awesome. Give yourselves, yeah, a pat on the back because you guys are doing an incredible job and we hope that you keep up the good work. And so what we've been able to do with those classifications is that I put this through a machine learning algorithm. It's called TSNE. And Isaiah has helped me with this as well. And so whenever we take all of those sources in our catalog, we put it in to the machine learning algorithm, which helps us visualize all of this data. And then we get a plot that kind of looks something like this. And you can see it's just a big black blob, really, right? We can't tell exactly what data is which. And so with all of your results, we can actually add color to this plot. And so what we've done is that Dark Energy Explorer probability, a 0 is a fake source, what you guys have said is bad. And then a 1 is a real source. And so that's what you guys have said is real. So if a 1, if it's completely blue, that means all 10 of you agreed 100%. This is for sure real. But if it's really dark red, then that means that's for sure fake. So then we can see from this black plot to this nice colored plot, we can see we have this congregated area of these nice fake sources that you guys agree on. And so we can then identify these regions here with the machine learning and where you guys have said they're fake, that these are where our bad detections or our false positives lie. And so then we can actually just remove those from our sample and we can just get rid of them. So these are the ones that we can remove. Then we have this nice clean sample of all of these galaxies that then we can use for the dark energy science that like Karl was talking about. So I will stop share and go back to our original slide deck here. So give me 1 second. I also meant to say that if you guys have questions, yeah, feel free to throw them in the chat or hang on to them and write them down because we want to make sure that all of your questions are getting answered. So yeah, just a few statistics that we have because you guys are so impressive. We saw in the chat whenever you guys were first arriving, where all you were coming from all over the world. And it's so awesome to see so much representation from people all over the world. Truly, you guys are doing so much for this project. So it's really cool. We have representation from 85 countries. And it seemed like we were covering a lot of ground just in this Zoom call. So that's awesome. We have about 12,000 volunteers like you guys And again, we're looking for about 1 million galaxies, but we're searching through 1 trillion data points. So we still have a long way to go. So there will be plenty of data for you guys to stay involved with. All right, awesome. So at this point, we would love to open it up to you guys. We would love to answer any questions that you guys have on the design competition, about classifying, general astronomy questions for Karl or anyone on the team, how HETDEX works, or questions about classifying, anything. We would love to throw your questions in the chat, or feel free to raise your hand or just unmute and ask the question.
Before we keep those questions in mind, to answer those few that came in late in the beginning, let's take a little quick detour. I have my Zooniverse website up, and let's look at one of the discussion posts, and let's discuss and see what we think it's either a keep or throwback. So this is going to be some raw image, and you'll get to see us discuss. So we're going to be discussing as team, and then we're also going to be all of you all discussing in the chat before we do this short Q&A. So give me 1 sec while I share my tab.
And let me make a comment again, because I've been hit with lots of professors who see us do this, and they say, why are you spending so much time with visual vetting? AI is the be all and end all of everything. Why can't you just use that? And of course, we have tried AI, machine learning. We've had some of the world's experts in this working on the project, and it does help. And as Lindsay showed, this visual vetting tied to machine learning is clearly the way to go. And we have such a tight spec on trying to keep our false positives down. That's why we need this extra kick of the visual to help out. So yes, we are doing machine learning, but it really is tied very closely to what you guys are doing.
And I was going to type this response, but I'll just say it out loud. So XY said, do we have a number we assess at any given time? So depending on your classifications, there is no finite limit. As Aaron pointed out, we did upload around 20,000 new data images for everyone to classify, apart if you haven't reached that maximum of like almost finishing those classifications. So it'll just keep going up until we have most of them done, if that answers that question. But before we answer more of the questions and such, let's go to my Zooniverse site, to the top page. This is by one of the users at Judea. If you're here, cool. If not, then we're gonna look at this image that was shared. Can everybody see this image appropriately? Like you can see everything on it. Yes? Okay, good. So let's take some time. Let's put it in the chat, just like in the beginning. Would you keep this galaxy or throw back? And if so, whichever the option is, why? Give us another like 30 seconds, and then you'll hear from us, the team, and see how we discuss it. So you can get a gauge of POV of how this works, I guess.
It's a beauty.
Definitely is.
I love this galaxy. And one thing we always have to point out, I look generally at the column on the left. The column on the right is the imaging. I really never use the imaging to throw a galaxy away. I'll use it to help me confirm, but it's just kind of a secondary consideration. So I'm mainly looking at the column on the left.
Yeah, so if I was classifying, because as researchers, as part of the team, we can also classify. And obviously it's important that we all have like sort of the same consensus or thinking logically. So yeah, I also look at the top left cut out images first. If I see that bright dark circle or like sort of that type of image, I would classify it as keep. But apart from looking at that section, I would then look at the bottom right to see that indicative bright spot and the bottom left to see that the error values are not like huge, but at least, I mean, they can be, the error can be a bit big in my personal opinion when I'm classifying, as long as they're not drastically like so far off and they're not even aligned with that curve. But yeah, I always look at the top left first. I don't know if any other team member wants to unmute and share. And definitely we're still keeping track of the chat of what y'all think.
And John has his hand raised too. So,
John, are you, I'm assuming it's
thanks.
for the question section.
Yeah, I had a question that actually went back to the point that Dr. Gebhardt made about the accuracy. Now, you mentioned the accuracy for detecting false positives for the visual observers was around 92%. Is there a number that's just for the AI, or do you have anything like comparative ROC curves between the visual observers and the AI at this point?
that's a good point. That's Lindsay's paper. That's Lindsay's thesis that we're working on. Lindsay, do you have an estimate at this point?
Sorry, to understand your question exactly, an estimate of what, John?
So if you just keep a TSNE, for example, what would the accuracy be in that box as it over the whole thing, as opposed to knowing what region to focus on?
Sure, yeah, over like for the false positives within just using TSNE.
Yeah.
Well, it's kind of hard because you saw the black blob. That's essentially what we're getting when we're just using TSNE. So we can't really see exactly where those false positives are lie. So it's really the combination of you guys and the machine learning that is shown to be the most accurate so far. So really just using the machine learning, just with TSNE, we're just getting that black blob, which is pretty unexciting. We can't actually see what these false positives are.
Just to follow up on John's point, what we really need to get to is what we call supervised learning, where we take what you all called as real, and then we tell the computer, okay, these are real, these are fake, then match them up. When we did that, we do a little bit better, but it's still not as good as the human eye.
Thanks. That's also helpful to wonder what's going to happen when medicine goes to AI to look at imaging studies, but that's another
I hope
topic.
It's not the same, that's right.
So me too.
Yeah, okay, so let me stop sharing for y'all. I'll let Lindsay go back to the Q&A slide in the meantime. But yeah, pointing out Deanna's question, what was it? The error. Yeah, so the error one is usually secondary, at least in my opinion. I would try to look at that top left images first. But as long as the error isn't too big and it tries to align as best as it can to the curve, that's like beautiful. That's what we want to see. But if it's not like perfectly aligned, just try to use the best as you can from the tutorial of what you learned of what you want to categorize as keep. And yeah, have fun with that. Bye. So questions. I know that there was various questions that maybe we didn't get to in the chat. So if y'all could put them again or raise hand function to unmute, please do so at this time. And we'll try to answer as a team. So one of the questions that we have is, I'll present this to the team, whoever wants to answer. From Lola asked, sometimes when I'm classifying the colored boxes, I'm assuming the top left corner has some white dots rather than the black dots. I know we've had this question in the discussion board and we've clarified it. If any of the team members would like to answer that question and clarify what the white dots are.
what we talk, I'm sorry, Jose.
Yeah, so I believe we got this question a while back with Aaron, and I think we had looked at it. So sometimes Lola asked that when she's classifying, sometimes the images have this white dot rather than the black dots in the cutout images. And
Right.
she was just, Lola was just wondering what those white dots are.
Yeah, I can't remember this specific example that we might have discussed, but usually if we're seeing white in those squares, which we call the fiber images, it probably means we have some sort of over subtraction going on. So most likely there's something wrong with the data and I would throw back, but it's hard to say without seeing it here. Anyone else remember what that was?
Yeah, so I believe we discussed this a bit ago. So not quite sure. However, I do have a general answer for that. Do classify it as throwback or keep. I'm not official. Do not, whatever you think fits align best with the tutorial. And then we also look at these classifications further from what you all classify. So we do further look into them, whether it's throwback or hashtag keep. So don't worry. And if it comes up, ask us and we can specifically look it up. And that's how we get responses back to you. So to clarify the discussion post, when one of the moderators researchers reply, we usually try to search up the detect ID, which is like the image that you all look at. And we look it up with HETDEX and such, and we try to determine the best response for all of you at that given time. But sometimes it may take longer processing and researching what the image actually is. So I hope that kind of clarifies. But yeah, if that ever happens, use the discussion, let us know and ask. And I'll let someone answer Vansh. I really like that question as well.
I tried to in the chat. I was saying math and be bold, Vansh, and we are stuck trying to understand what dark energy is. And you know, I like to think that we're kind of stuck in a rut in terms of theory and trying to figure out what's going on. We really need people coming, as I say, thinking outside the box. Don't live out the box, but you can think outside the box. That's kind of what we need. So Julia has her hand up there.
Hi, everybody.
Hi.
I had a kind of general question, and it maybe follows on from what you were just saying. I imagine there's other groups out there in the world looking at dark energy. What kind of things are they doing? Yours is, I guess, you know, collecting data.
Yep.
Are there other approaches that people are using?
So, well, we're all basically doing the same thing. When you want to measure the expansion of the universe, we use individual galaxies, measure how fast they're moving away from us, measure how far away they are from us, and then you can get the expansion rate. What sets HETDEX apart is we're looking way in the past. So when the universe was very young, 10 billion years ago, we're doing that because when we designed this 20 some years ago, we knew that these other experiments were going to come along and they were observing the universe nearby. And we said, okay, we can play the game. Do we want to just do more of the same nearby, get a better measurement, or go to a new epoch in the universe? There was a question that someone asked in the chat, I didn't get time to respond to. They said, does dark energy vary over time, or is it consistent with a cosmological constant? And the problem with that is there's really only been one epoch in the universe where we've measured the expansion rate. That's about 2-3 billion years ago. And all the experiments are trying to nail that down to better and better value. HETDEX, this is where we're, I talked about thinking outside the box. We're using a whole new epoch 10 billion years ago, and we're going to turn that one measurement of how fast the universe is expanding to two measurements at two different times and look at the differential. So Julia, they're all we're doing the same thing, but we're looking very far away. Partly why we can do that is we built this crazy spectrograph, and we're using the Hobby-Eberly telescope just behind Lindsay's head there, which is one of the biggest telescopes in the world. And that's our unique advantage. We're playing to our strengths that we own this telescope, and we're from Texas. And so everyone knows we go big.
Yeah, absolutely. Thank you for that. Thanks.
And then as we're tracking the chat, okay, so HETDEX will probably okay, so we're probably going to cover the instrumentation and such, but HETDEX looks at dark energy specifically out in the universe. So as of now, Dr. Gebhardt and the team are not looking at JWST data from what I know, specifically with HETDEX dark energy exploring. So that should answer John's question. However, if anyone has further input, they can for sure tell me otherwise.
Well, I'll just say that we've actually taken a lot of data that does cover what we call some of these legacy deep fields that JWST is devoting a huge chunk of time to. So just because, we're actually, surveying a huge chunk of the sky, we're going to have so much data that overlaps with JWST. So we do expect to have some really exciting overlap and results coming out by comparing our survey. It won't necessarily be about the cosmology, but there will be a lot of galaxy evolution studies that we'll do, and it's going to be awesome.
One note on all you dark energy explorers is that because you've done so well, we're going to push it even more. So the next set of sources that Aaron just put up there are a little harder, a little lower signal to noise. And that's where a lot of our sources come from. And so we're going to try to see how well we can do with visual vetting in this new regime. So this is kind of, we're testing each other. We want to, it's this back and forth. That's what the science is about. So we'll see how that goes.
Yeah, and then to answer or partly answer, and then anyone else can also chime in. Gregorio asked, could there be a connection between dark energy, dark matter, and how gravitational waves propagate? So just to clarify, dark energy is the acceleration expansion of our universe, whereas dark matter is believed to be the same amount since the Big Bang. However, I'm not sure exactly how it connects to gravitational waves propagation. Well, actually, I think I do, but I'm not going to answer that. I'll let anyone else answer if they have a response to that.
Both gravitational waves and photons travel at the same speed. They travel at the speed of light. And so dark energy will affect the gravitational wave just as much as it affects a photon. If the universe is expanding, it'll take longer for that gravitational wave to propagate. In fact, one thing that's very exciting, it's probably going to happen about 5 or 10 years from now. The Gravitational Wave Observatory, once they turn it back on, should be able to detect distances very accurately. And the expectation is they are going to absolutely nail how fast the nearby universe is expanding, way more than the experiments that are ongoing. Again, HETDEX will stand alone because we won't be able to see the gravitational waves that we need to, at those very high distances. So that will be a really powerful anchor once they do that. But yeah, the gravitational waves are affected just like anything else.
Yeah, so dark energy, dark matter contribute to changes in our universe, but we can't see it is the main thing. So I believe
Diana's question is really good. I'll answer that one, or we can get into that. I don't know if there's examples, but we've got not a lot of time left. But yeah, so we have uploaded the new 20K that have been uploaded are at slightly lower signal to noise, which means that the dots are going to be fainter. You might not see dots in all of the fiber images, those colored squares. And the line, the spectral line, the emission line at the bottom, it just won't have as much signal, but you'll be looking for really the same features that you've already been looking for, dots in at least one or two of those fiber images and a nice line. There will be less what we call high line width broad features, so less AGN that are kind of confusing, but you'll see, you won't always see a dot. And if you don't see dots, just like in that very first example, it's a tough one because it looked good at the bottom, but if you don't see any dots, throw it back. It's probably not real. You know, and it's okay if you get it wrong. We're going through a whole bunch of different methods to try to validate these sources.
I want to say, oh, go ahead.
No, go ahead.
I was just going to say, you're looking at the team right now that does all the work. And this is, you know, it's a $42 million experiment. There's probably on our scientific emails, there's probably, you know, 100 people who signed up for the emails. There's probably 20 people who are interested in the cosmology, and there's probably the handful here that are working with us who do all the work. And so it's the efforts from you that is really adding on to our team base. And so again, as Aaron says, you know, we're trying something new here, and we're going to use this as an experiment on both of us, you and us.
Yeah, that's so true.
Yeah. Oh.
And I just wanted to remind you guys really quick, I know we don't have much time left, of our logo design competition. We would love to try and get some from you guys to make eventually, hopefully, some stickers or some cool merch that we can have as Dark Energy Explorers. We also have a survey, and Jose, if you'll throw that in the chat for people, we would love to just get some feedback from you guys on things maybe you want to hear in this call. Maybe next time you want to learn more about the telescope or something like that. We would love to hear what you guys are looking for and learning from us. And last but not least, I would also love, if you guys feel comfortable, I'll stop sharing my screen right now. I would love to invite you guys, if you feel comfortable, to turn your camera on so that we could take a picture of all of our Dark Energy Explorers. If you feel comfortable, no pressure at all. But I think it's been really awesome to see such an incredible turnout from all of you guys from all over the world. And we really, really appreciate all of the work that you guys have been doing. So thank you. And it's so great to see all of your faces as well. Thank you so much. So awesome. Cool. Yeah, and Jose, thank you for putting the feedback form in the chat. If you guys have a chance to get that feedback form, we would really appreciate it. It will only be here, but if not, we'll stay on, answer any more questions that you guys have, but we hope to see you maybe at the next one of these. And we thank you guys so much for all of your awesome work and spending your Monday night with us.
Thanks all.
Yeah, thank you so much. Please look at the chat. The chat has a survey. We'll try and manage and see how we can send it to all of you, but it's kind of difficult to track the participants that came. But in the survey, it's very quick. Don't worry for those that are still here. It's a very quick survey, 5 questions. We just want to get to know where we can improve, what you like, maybe what you didn't like. If you didn't like our Zoom night, I hope you did. It was amazing. And yeah, just let us know what you'd like to see. There's also a question of like, do we have events with citizen science volunteers like all of you? What you want to see? Do you want to hear the instrumentation? Is there a specific topic with HETDEX? So yeah, I'll put that in the chat again. And as Lindsay said, if anybody has remaining questions, we'll be here for a little bit.
Yeah, thanks for coming, guys.
Yep. Keep it up. Rock on.
Thank you. Bye.
Bye.
Thanks.